I'm Petra Wolf from the University of Trier, giving a talk about synchronization under dynamic constraints. One of the motivations for synchronizing automata from the 1980s was the problem of designing parts orienters for assembly lines. The image on the left is taken from the work of Natarajan from 1986, who first modeled designing parts orienters as synchronizing an automaton. In the problem of parts orienter, we have an assembly line where parts are coming in an unknown orientation, but one still wants to work with the parts in a predefined orientation, and due to lack of expensive sensors, we cannot observe the initial orientation, but we still want to find a sequence of modifiers such that we can bring the initial part into a predefined orientation. And in this example, the modifiers consisted at jumps of a certain height, or they can consist of wall against which the tile slides, and so on. And what Natarajan did is he modeled the possible orientations as states of an automaton, and the modifiers, like small jumps, as letters. And then the problem of finding a sequence of modifiers that brings part from any possible initial orientation into a well-defined orientation corresponds to finding a sequence of letters which map each state of the automaton to one single state. But what this formalization does not take into account is that the modifiers can have some impact on the parts. So here it is assumed that after the jump, the part itself is still intact, and that it's still in the same form as before the jump, only the orientation has changed. But this might not always be the case. For instance, if we consider a box with lids which can be open or closed, then changing the orientation of the box might cause the lids to fall open. For instance, if we now use a jump modifier to bring this box in an up-facing orientation, then we end up with an open lid which we have to close again, and if we continue to modify the orientation, we might cause the lids to open again. So, but if we now want to end up with an orientation where the box is facing upwards and the lids are closed, we somehow have to encode the condition that when the state facing sidewards is reached, we later have to reach the state where the lids are closed. But this does not prevent us from opening the lid again. So what we really want to have is that after the last time the box was in the state sideward facing, it needs to visit the state lid closed at least once. So what we are doing here is we are comparing the last times a state is reached. And if we compare the last appearance of states, then in a sense we're adding positive constraints to the behavior of the automaton, in a sense that whenever I reach some state, then later on I have to reach another state. But we can also do the contrary, in a sense, adding negative constraints, meaning that whenever I reach a state, I later cannot reach some other state again. And this can be motivated by the following example, that we have a box where the lid is closed and we have some mechanism keeping the box closed. And later on, we want to end in a position where the box is open, but the content of the box is still in it. So hence we have a modifier which opens the lid. But if we would now continue to rotate the lid, so hence if we would now go into a state where the box is facing sidewards, then we would cause the content of the box to drop out and we could not reach our final orientation. So what we want to do here is we want to add the constraint that as soon as we entered the state where the lid is open, we are not allowed to enter the states facing sidewards again. In order to formalize our observations from the examples, we first need to define the two functions first and last, which take as input in a state, a word, and a set of states. And for instance, the function first then returns the minimum of all positions at which the state Q, the input state, appears as an active state while reading the input word W on all states of the input set S. And if the state Q does not appear at all while reading W on S, then we set the default case of the function first to a position which is higher than any position of a state actually occurring, meaning that we set it to the length of the word plus 1. Similarly, we define the function last on the same input as returning the maximum of all positions at which the state Q appears. And here we set the default case to -1, meaning to a value which is lower than the return value of all states which do actually appear. And if we now consider this example to get a feeling for this function, during the whole talk, we will consider this example automaton together with this example input word BAB. We are starting to count at position 0, so if we have not read any input letter, we're in the position 0, and reading an input letter causes an increase in the position. So let's consider some examples. First, consider the first position at which the state 3 appears as an active state when we read our input word BAB on the state set 1 and 2. Then it turns out that the state 3 first appears at position 2. On the other hand, if we ask for the first position on which the state 5 appears while reading our input word BAB on the state set 1, 2, then we notice that the state 5 never actually appears as an active state, and hence our default case comes into place, meaning that the return value of the function is the length of the word plus 1, and hence position 4. On the contrary, if we consider the last position at which the state 2 appears, if we consider reading the input word on the whole state set, then we notice that this position is position 3, since the state 2 is our final synchronizing state. On the other hand, if we want to know the last position on which the state 5 appears, again on the set 1, 2, then again we notice that the state 5 does not appear at all, and hence the default case takes into place, and we return the value -1. Now, equipped with these two functions, we can formalize our conditions from the examples by defining how a word can imply an order on the set of states. This is simply our symbol we will use for P is in relation to the state Q. The subscript W is the input word by which the order is implied, and we notice whether we're considering sets or paths, more on that later, as the subscript S. And on top, we describe whether we're comparing the last positions or first positions or combinations thereof. So in the first variant, we are comparing the last occurrences of two states, and we say that the state P is related to the state Q if the last position on which P occurs while reading W on the whole state set is strictly smaller than the last position on which Q appears. In the next version, we say that the state P is related to a state Q if and only if the last position at which the state P appears while reading W on the whole state set is smaller or equal than the last position of Q. And now let's consider some examples to get a feeling for these two relations. So for instance, for both variants, strictly smaller and smaller or equal, we have that the state 3 is related to the state 2, meaning that the last occurrence of the state 3 is smaller than the last occurrence of the state 2, because 2 is also appearing in the last position 3, but the state 3 disappeared one step earlier, and hence the last position of 3 is smaller than the last position of 2. On the other hand, if we consider the strictly smaller case, then we have that the state 1 is not related to the state 3, while in the other case, when we allow equality, then both variants are related. So 1 is related to 3 and 3 is related to 1, because these two states disappear simultaneously. So the first variant basically means that at some point the state 3 needs to appear without the state 1, which is not the case in our example. One pair which is not related in both orders is 4 and 5. Now we have so far considered the whole state set, so we're basically considering sets. But the fact that we are starting in the whole state set at once comes from our lack of knowledge about the actual state. So what we have here now is that we're basically relating states appearing at one pass with states appearing at the completely different pass, and which might have no connections whatsoever on the same path. So what we basically want to do is we want to track the path individually and make sure that the order in which the states appear on the single path map with our restrictions. So let's also define a variant of this order considering paths instead of states. So we're still comparing the last positions at which states appear, but now we are not considering the whole state set, but singleton sets. And we demand that this relation holds on each path. So, and to get a feeling where the difference lies, let's again consider some examples. So since we are now considering single paths, we need to have the image of every state, so we can no longer consider sets, but we now need to consider single paths. And again, we have that the state 3 is related to the state 2 in both variants. Then a difference to the version before is that before, in the less or equal case, we had that both 1 is related to 3 and 3 is related to 1. This is no longer the case if we consider paths, because now we need to have that on every path we have that the last position of 1 is smaller than the last position of 3. While this is true for the first 3 paths, this is no longer true on the 4th and 5th path, because when we track the state 4, then we reach the state 1 at some point, but we never reach the state 3. And the same holds for the other direction, because, for instance, on this path here, we have that the state 3 appears, but the state 1 does not appear. And also one difference is that if we consider the previous case on sets, we would have that for the strictly smaller case, the state 5 is related to the state 1, since the state 1 later appears without the state 5. But this is no longer true on paths in the strictly smaller case, because in the strictly smaller case, we demand that the last position of the bigger state is strictly bigger than the last position of the smaller state. And in the case that neither of these states appear on the path, we would have for both cases that the position is -1, and hence the positions are equal and not one is strictly smaller than the other. So what we basically have in the strictly smaller case is that for each bigger state, the state must appear on each path finally. So far we only compared last positions of states, but we also had this introductory example where we implied negative conditions on future state visits, meaning that the visit of one state forbids for the visit of another state, and that is what we want to formalize next. And we now say that the state P is related to a state Q if the last occurrence of P is smaller than the first occurrence of Q. And this order we will only consider on path, since if we would consider it also on sets, then already in the initial configuration where the whole state set is active, we would violate any pair, so no pair of states would be related. So again, let's consider some example and look what is different now than with the orders before. So in all previously considered cases, we had that the state 3 is related to the state 2, since 2 is the final synchronizing state. This is no longer the case if we consider this order here, where the first visit of the state 2 forbids for future visits of the state 3. And this is violated by the path in the middle, where we start in the state 3 and go to the state 2, so the state 2 is reached. And now we're no longer allowed to reach the state 3 again, but we actually do by reading an A. On the other hand, what was also similar before is that if we consider the state 1 and 3, then either both variants were related, meaning that 1 is related to 3 or 3 is related to 1. But this is no longer the case for this order, because here these two pairs behave differently. On the one hand, we have that 1 is related to the state 3, since we do not visit the state 1 after visiting the state 3. But on the other hand, we do actually visit the state 3 after we visit the state 1. In the first path here, we visit 1, and later on we visit the state 3. Another similarity what we had before is that the state 4 was not related to the state 5. But if we consider now the last position of 4 with the first position of 5, then this pair is actually related, because we never visit the state 4 after we have visited the state 5. So now we have to find a set of orders which we now want to relate to the synchronization problem. So the problem we will consider in this talk is called synchronization under order, and now insert for this symbol here, insert one of our predefined orders. And what we are considering is we're given as input deterministic complete automaton consisting of a state of sets, an input alphabet, and a transition function. We are not considering initial or final states, since we're only interested in synchronizing this automaton. And we combine this input automaton with a binary relation on the state set. And we ask whether there exists a word that synchronizes the automaton, meaning that it maps all states to one single state, such that the input relation R agrees with the order implied by the synchronizing word W. And we will also consider the subset synchronization variant, where we are not only given an input automaton and a binary relation, but we're also giving a subset of states, and we want to know whether there exists a word that needs to only synchronize the subset, but again, the input relation should agree with the order implied by the synchronizing word. So far, we have not restricted the input relation in any way. We just allowed any binary relation, but we will also consider a special case where we demand that the input relation is a strict and total order on the set of states. One aspect we have not discussed so far is the following. If we consider the concept of synchronization, then our initial configuration is strict. We always start with the whole set of active states, and one can argue now whether we want to take this initial situation into account, meaning that already this fixed situation implies some constraints on the sets we can or must reach, or whether we want to only consider the actual whether we want to consider only the actions really implied by the letters we read. So now we have defined everything we need to state our results. So we were basically looking at the complexity of these problems, and we noticed that in the case when we consider sets, in both variants we observe that the problem is p-space complete. Whereas if we are considering paths, then in the simple synchronization problem, we can observe a drop in complexity if we go from sets to paths in the version that we demand that the last occurrence of the smaller state is strictly smaller than the last occurrence of the bigger state. On the other hand, if we also allow equality, then the case is not so clear. So here, for taking the initial position into account, we only could observe NP hardness, but we do not have membership in NP, so we don't know whether these two cases are really different. Whereas in the special case that our input relation R is a strict and total order, and we're considering negative restrictions, then these two versions, meaning considering the initial situation at position 0 or starting at position 1, are different if we're considering path. All of these observed differences vanish if we go from normal synchronization to subset synchronization, because here, for these cases, we observe p-space completeness, and in the case that R is a strict and total order, we observe NP completeness, and also this difference here now disappeared. In the case that the last position of the first state is strictly smaller than the last position of the second state, this problem is actually contained in NP. And this comes from the following observations, that for a pair of states, which is contained in the input relation, we must have that the state Q appears finally on the path, since we demanded that the last position of Q is strictly bigger than the last position of P. And since we're by definition demanding that this is the case on all paths, meaning that regardless of where we start, we must have that the state Q is reachable from any state in the set of states. And since we only compare the last appearances of states, we can first synchronize the whole automaton and later check that we go through the related states in the demanded order with the remaining state. We now arrived at the last result I wanted to present. If you remember the table of results, we had one entry which claimed that the problem is solvable in polynomial time, and this was the case for the order where the visit of some states forbid future visits of the smaller states. In the version that we also consider the initial configuration, meaning that we start at position 0, and we have that the input relation R is a strict and total order. And how do we do this? Well, since R is a strict and total order, we can simply order the states according to R, and then we can delete all transitions which would violate the input relation R, because in the considered variant of the order, we cannot repair a forbidden state transition in the future as we can with comparing last positions, and hence we simply can globally delete all transitions which would violate a pair in R, since R is a strict and total order. Next, assume the state Qn is the maximal state with respect to R. Then we can also delete all transitions globally, which are undefined for the maximal state Qn. Then we come to the main part of our algorithm, that is that we repeatedly will track the subset of input letters which are defined on all active states. And then we go through all the active states in order and test whether one of these defined input letters leads to a bigger state. If so, then we apply this input letter, and we also apply the previously constructed prefix of a synchronizing word. And we will end up finally with a singleton set of active states and a synchronizing word if and only if one exists. Well, now one could argue that, well, this is a very special case of the problem, so why should I care about this result? But it turns out that this actually implies an interesting result for the subclass of weakly acyclic automata. And the weakly acyclic automaton is deterministic finite automaton such that there exists an order on the set of states such that all transitions are leading to bigger states. And the class of weakly acyclic automata is a subclass of the class of aperiodic automata. And we have that the previously considered synchronization under order variant is equivalent to the careful synchronization problem for partial weakly acyclic automata. And hence, since this problem is solvable in polynomial time, also this problem is solvable in polynomial time, which is quite surprising since the careful synchronization problem is a very hard problem in general. And also, if we consider subclasses of automata, there the careful synchronization variant also remains hard, in most cases p-space hard, in other it drops to NP hardness, but none subclass that I'm aware of has a polynomial careful synchronization problem, but now we found one for with the weakly acyclic automata. Now I want to conclude with again showing a summary of our results, and I thank you very much for listening and see you in the Q&A session.